Hello and good day. This report is on the z-test, the t-test, and the f-test. The ability to estimate population parameters or to do test hypotheses about population parameters using sample statistics is one of the main applications of statistics in improving decision making. Whether estimating parameters or testing hypotheses about parameters, the inferential process of the inferential process consists of taking a random sample from a group or body, which is the population, analyzing data from the sample, and researching conclusions about the population using the sample data. In the hypothesis testing process, the known parameter is assumed to be true. Data are gathered from random samples taken from the population, and the resulting data are analyzed to determine if the parameter value is still true or has changed in some way. Questions that could be asked are, for example, does the average worker still work 40 hours per week? Are 65% of all workers unhappy with their job? Like with confidence intervals, hypothesis testing can be used to test hypotheses about means, proportions, and variances, and other parameters. Because there is a plethora or an assortment of, or toolbox, so to speak, of um, hypothesis testing techniques, we may lose the big picture of when to use what technique. To assist us in sorting out these techniques, this figure shows a taxonomy of techniques has been created and is presented in a tree diagram for our convenience and consideration. Note that in determining which technique to use, there are several key questions that we should consider. Number one, are we estimating or testing? For estimating, we'd be using confidence intervals, and for testing, we'd be using the hypothesis tests. How many samples are we analyzing? Are you analyzing means, proportions, or variances? If we are analyzing means, is the standard deviation or variance known? If we are analyzing means, from two samples, are the samples independent or related? So these are our questions, or the questions that we should be considering on what hypothesis test to use, if we're going to use z-test, t-test, or f-test. So for z-test, what kind of z-test? Z-test for a single sample population or a two sample. It's the same with the t-test. So I'm going to remove these two legs from this part of the tree diagram, put it in the next slide as so. So these are the statistical tests that we will be tackling for this report. Z-test, t-test, and f-test for a single sample and two sample population. A foremost statistical mechanism for decision making is the hypothesis test. The concept of hypothesis testing lies at the heart of inferential statistics, and the use of statistics to prove or disprove claims hinges on it. With hypothesis testing, researchers are able to structure problems in such a way that they can use statistical evidence to test various theories about any phenomena. The next few slides contain techniques for testing hypotheses about a population mean, population proportion, and population variance. Note that at the bottom of each tree branch, the title of the statistical technique is given for ease of identification and use. If a researcher is testing a population mean and the population standard deviation is known, then he or she will use the z-test for mu. If the population standard deviation is unknown, and therefore the researcher is using the sample standard deviation, then the appropriate technique is the t-test for mu. If a researcher is testing a population proportion, this one, then he or she will use the z-test for P. We could summarize 8 steps on performing hypothesis test. 1. Establish a null and alternative hypothesis. Step 2. Determine the appropriate statistical test. Step 3. Set the value of alpha, which is usually given. Step 4. Establish the decision rule. Step 5. Gather sample data, which is also given. Step 6. Analyze the data. Step 7. Reach a statistical conclusion. And step 8. Make a decision. So the first hypothesis test that we're going to study is the z-test. The z-test for mu. One of the most basic hypothesis tests is a test about a population mean. A business researcher might be interested in testing to determine whether an established or accepted mean value for an industry is still true, or in testing a hypothesized mean value for a new theory or product. As an example, a computer product company sets up a telephone service to assist customers by providing technical support. The average wait time during weekday hours is 37 minutes. However, a recent hiring effort added technical consultants to the system, and management believes that the average wait time decreased, and they want to prove it. Other scenarios resulting in hypothesis test of a single mean might include the following. Example, a financial investment firm wants to test to determine whether the average hourly change in Dow Jones average over a 10-year period is positive 0.25. Another example would be a manufacturing company wants to test to determine whether the average thickness of plastic bottle is 2.4 millimeters. Or a retail store wants to test to determine whether the average age of its customers is less than 40 years. This formula can be used to test hypotheses about a single population mean when sigma, or the population standard deviation, is known, if the sample size is large and is greater than or equal to 30 for any population, and for small samples, if x bar, or the sample mean, is known to be normally distributed in the population. If the hypothesis test for population mean is being conducted with a known finite population, so n is finite and is known, capital N, the population information can be incorporated into the hypothesis testing formula and results with this one. Doing so can increase the potential for rejecting the null hypothesis. However, if the sample size is less than 5% of the population, the finite correction factor does not significantly alter the solution. So the formula can be amended to include the population information. So how are we going to use these formulas? Let's look at an example. So for this one, in an attempt to determine why customer service is important to managers in the United Kingdom, researchers surveyed managing directors of manufacturing plants in Scotland. One of the reasons proposed was that customer service is a means of retaining customers. On the scale of 1 to 5, with 1 being lowest and 5 being highest, the survey respondents rated this reason more highly than any of the others, with a mean response of 4.3. Suppose US researchers believe American manufacturing managers would not rate this reason as highly and conduct a hypothesis test to prove their theory. Alpha is set at 0.5. 0.05, or that's 5%. Data are gathered and the following results are obtained. Use this data and the 8 steps of hypothesis testing to determine whether US managers rate this reason significantly lower than 4.3 mean. So that gives us an idea that that is our alternative hypothesis. This reason significantly lower than 4.3 mean ascertained in the United Kingdom. Assume from previous studies that the population standard deviation is 0.574. So what is step one? Establish hypothesis. Because the US researchers are interested only in proving that the mean figure is lower in the United States, the test is one-tailed. Because our alternative hypothesis is or has a symbol of less than, even if it is greater than. No? We will only perform a two-tailed test if the null, or I mean if the alternative hypothesis is not equal to. So that is our alternative hypothesis, that the population mean is lower than 4.3. The null hypothesis states the equality case. Okay. So step 2, determine the appropriate statistical test. The test statistic is z-test for mu, because sample size is larger than 30 and standard deviation is known, or at least the population standard deviation is known. Step 3, specify the type 1 error rate. Alpha is 0.05. Okay, so that's given. State the decision rule. Step 4. Because this test is a one-tailed test, the critical z value is found by looking up 0.45. So where did we get 0.45? Subtract 0.5 with 0.05, which is our alpha. Why 0.5? Because it's a one-tailed test and 0.5 signifies one half of our bell curve. Okay. So 0.5 minus 0.05 is 0.45. As an area in the table 8.5. So table 8.5, link a I'll put a link in the description. What is table 8.5? So table 8.5 is a z table. So we're going to look at 0.45 in the z table. So the critical value of the test statistic z0.5 would be negative 1.645. An observed test statistic must be less than negative 1.645 to reject the null hypothesis. The rejection region and critical value can be depicted in the following diagram. This one. Okay, so this is our bell curve, divided in between by z is equal to 0. We mark z of 0.05 equal to 1.645 right here. Okay. So below this one, this is the region of rejection. So between this one, or after, I mean, all values greater than this one, right here, this is the region of non-rejection. If our observed test statistic will fall inside the non-rejection region, so we're going to uh, accept our null hypothesis. So step 5, let's gather the sample data. So based from this data, this one, we're going to compute for the sample mean and sample standard deviation. Sample mean and sample standard deviation would be 4.156 and 0.574. So the only thing that we're going to do now is substitute these values to our z formula, this one. Because everything else is given, we could automatically get the value for z, or observed test statistic, to be negative 1.42. So where does negative 1.42 lie in our curve? It's after negative 1.645. So it's between, or it's inside the non-rejection region. So action, step 7. What is our statistical conclusion? Because the observed test statistic, negative 1.42, is not less than the critical value and is not in the rejection region, the statistical conclusion is that the null hypothesis is not rejected, cannot be rejected, or we fail to reject our null hypothesis. So what is the implication of our statistical conclusion to our problem? The test does not result in enough evidence to conclude that US managers think it is less important to use customer service as a means of retaining customers than do UK managers. All right. So, although this is just an example for the z-test for mu, these 8 steps somehow gives us a picture on how to also solve all the other, all right, all the other uh, hypothesis tests. So this is the framework now for solving any hypothesis test. Steps 1 to step 8. So the vital thing that we're going to actually do when we perform hypothesis test is to point out all the given, you know, to determine the appropriate statistical test and plug those values only to our formula. So, and that's it. Okay. Actually, that's the only hard part of our hypothesis test. Plugging the values to our formulas. Okay. So let's move on to the next test, the t-test for mu. Very often, when a business researcher is gathering data to test hypothesis about a single population mean, the value of the population standard deviation is unknown, and the researcher must use the sample standard deviation as an example, as an estimate of it. In such case, the z-test cannot be used. The t-distribution can then be used to analyze hypotheses about a single population mean when sigma is unknown, or the population standard deviation, if the population is normally distributed for the measurement being studied. In general, this t-test is applicable whenever the researcher is drawing a single random sample to test the value of a population mean. The population standard deviation is unknown, and the population is normally distributed for the measurement of interest. Also take note that the sample size should be relatively small, less than 30. The formula for testing such hypothesis is as follows. So we have the formula for T and the formula for DF, or the degrees of freedom. So let's look at another example on how to perform t-test. Figures released by the U.S. Department of Agriculture showed that the average size of farms has increased since 1940. The mean size of farm was 174 acres by 1997. The average size was 471 acres. Between those years, the number of farms decreased, but the amount of tillable land remained relatively constant, so now farms are bigger. This trend might be explained in part by the inability of small farms to compete with prices and cost of large-scale operations and to produce a level of income necessary to support the farmer's desired standard of living. Now, suppose an agribusiness researcher believes that the average size of farms has now increased from 1997 mean figure of 471. So that gives us an idea on what our alternative hypothesis will be. The average size has increased. To test this notion, she randomly sampled 23 farms across the United States and ascertained the size of each farm from country records. The data uh, she gathered is as follows. Use a 5% level of significance. So these are our data, 23 samples. Our null hypothesis would be mu is equal to 471 and alternative mu is greater than 471 because the agribusiness researcher believed that the average size has increased. And we're going to use the t-statistical test. Alpha is 0.5, degree of freedom, minus 1, and is 23 minus 1, that's 22. So we're going to look up these two values in our t table. So it's another table. Degree of freedom of 22 and alpha of 0.5. So that value will be 1.717. So this 1.717, where is this on our bell curve? It's right here. Okay, so above 1.717, that is our region of rejection. Okay? So after gathering the data, computing for the sample mean and the sample standard deviation, plugging everything to our formula, we obtain an observed t-value of 2.84. Where is 2.84? It's above the 1.717 p-value. Okay? So what is our decision? We reject the null hypothesis. The observed t-value is 2.84 is greater than the t-value of 1.717. So the business researcher rejects the null hypothesis. She accepts the alternative hypothesis and concludes that the average size of US farm is now more than 471 acres. Okay? So I hope that's understandable. And these two examples will be representative of all the other z-tests and t-tests that we're going to be covered. Okay? So although there are many kinds of z-tests and many kinds of t-tests, the steps are all the same. Okay? As long as everything is given, we have the z-table and t-table, we have the formula, plug everything to the formula, compare the value obtained from the formula to that of the tables, and now we could create our conclusion. Okay? So how about for tests of proportion? Data analysis used in decision making often contain proportions or percentages to describe such aspects as, for example, market share, consumer makeup, quality defects, on-time delivery rate, profitable stocks, and among others. Surveys often produce information expressed in proportion form, such as 0.45 of all businesses offer flexible hours to employees, or 0.88 or 88% of all businesses have websites. Researchers conclude hypothesis tests about such proportion to determine whether they have changed in some way. Another example, suppose a company held a 26% share of the market for several years. Due to a massive marketing effort and improved productive product quality, company officials believe that the market share has increased and they want to prove it. So those are some examples of situations of when we are going to use the z-test for proportion. This formula for inferential analysis of proportion will be used. Based on the central limit theorem, this formula makes possible the testing of hypotheses about the population proportion in a manner similar to that of the formula used to test sample means. Recall that p hat denotes a sample proportion and p denotes the population proportion. To validly use this test, the sample size must be large enough such that the product of n and p and n and q would be greater than or equal to 5. So that is the z-test for population. Here's an example of how the z-test for population can be used. So this could be studied on your own time, but this is quite similar to that of how we perform z-test for mu, or the z-test for mean. So observe that we are going to still use the 8 steps to perform hypothesis test. So that would be our framework on performing hypothesis tests. Okay. As long as, again, I'm going to reiterate, as long as everything is given and we have the formula and we have the tables, okay, available, everything is already set. And hypothesis testing is as easy as anything. So that's it for hypothesis test from 1 samples. How about hypothesis test for 2 samples? We have 5 tests for those, z-tests and t-tests and an f-test. To this point, all discussion of hypothesis test has centered on single population parameters. That is, a single sample is randomly drawn from a population, and using data from that sample A population mean, proportion, or variance is tested. Often, it is of equal interest to make inferences about two populations. A retail analyst might want to compare per person annual expenditures on shoes in year 2009 with those in year 2006 to determine whether a change has occurred over time. A market researcher might want to estimate or test to determine the proportion of market share of one company in two different regions. From here, we will consider several different techniques for analyzing data that come from two samples. One technique is used with proportions, one is used with variances, and the others are used with means. The technique for analyzing means are separated into those using the z statistic and those using the t statistic. In four of the five techniques that will be presented, the two samples are assumed to be independent samples. The samples are independent because the items or people sampled in each group are in no way related to those in the other groups. Any similarity between items or people in the two samples is coincidental. One of the techniques then is for analyzing data from dependent or related samples in which items or persons in one sample are matched in some way with items or persons on in the other sample. So this will be discussed in detail later. The tree-diagram taxonomy of inferential techniques are organized by usage of number of samples and the level of data. The following contain techniques for testing hypotheses about the differences in two population means and two population proportions, and in addition, testing hypotheses about two population variances. The rightmost branch of this side, right here, this one, contains and displays the various hypothesis testing techniques. The central branch of this figure contains techniques for testing hypotheses with two samples. Note that at the bottom of each tree branch, the title of statistical technique is given for ease of identification and use. If a researcher is testing hypothesis about the difference in two population means and the population standard deviation is given or known, then he or she will use the z-test for differences of means. If the population standard deviation or variances are unknown, then the proper technique is the t-test. This one. If the researcher desires to test a hypothesis about two population variances, then he will use the f-test. Okay? So first off, the z-test for mu1 minus mu2. In some research designs, the sampling plan calls for selecting two independent samples, calculating the sample means, and using the differences in two sample means to estimate or test the difference in the two population means. The object might be to determine whether the two samples come from the same population or if they come from different populations, to determine the amount of difference in the populations. This type of analysis can be used to determine, for example, whether the effectiveness of two brands of toothpaste differs or whether two brands of tires wear differently. Research might be conducted to study the difference in the productivity of men and women on an assembly line under certain conditions. An engineer might want to determine difference in the strength of aluminum produced under two different temperatures. Does the average cost of two-bedroom, one-story house differ between one city and another? If so, how much is the difference? These and many other interesting questions can be researched by comparing the difference in two sample means. How does a researcher analyze the difference in two samples? By using sample means. The central limit theorem states that the difference in two sample means is normally distributed for large sample sizes. Both n1 and n2 should be greater than or equal to 30, regardless of the shape of the population. This formula is the basis for statistical inference about the difference in two means using two random independent samples. If the populations are normally distributed on the measurement being studied, and if the population variances are known, this formula can be used for small sample sizes. In many instances, researchers want to test the differences in the mean values of two populations. As an example, a consumer organization might want to test two brands of light bulbs to determine whether one burns longer than the other. A company wanting to relocate might want to determine whether a significant difference separates the average price of homes in Cagayan de Oro from home prices in Iligan. The formula can be used to test differences between two population means. Okay. So here's an example. The process of which is very similar to that of the z-test for single mean population. T-test for mu1 minus mu2. The techniques from the previous slides used whenever the population variances are known. In many occasions, statisticians test hypotheses about the difference in two population means and the population variances are not known. If the population variances are not known, the Z methodology is not appropriate. This slide presents methodology for handling the situation when the population variances are unknown. That is sigma 1 and sigma 2. The hypothesis test presented in this slide is a test that compares the means of two samples to determine whether there is a difference in the two population means from which the sample comes. This technique is used whenever the population variances are unknown, hence the sample variances must be used, and the samples are independent or not related in any way. An assumption underlying this technique is that the measurement or characteristic being studied is normally distributed for both populations. This formula is constructed by assuming that the two population variances, sigma 1 squared and sigma 2 squared, are equal. Thus, to test the hypothesis about the difference in two means from small independent samples when the population variances are unknown, we must assume that the two samples come from the populations in which the variances are essentially equal. That is, sigma 1 squared is approximately equal to sigma 2 squared. Note that if the equal variances assumption cannot be met, the following formula should not be used. Or no, I mean, if the sample variances assumption cannot be met, then this next formula should be used. Okay, the bottom portion of the slide. Because this formula requires a more complex degrees of freedom component, it may be unattractive to some users. Many statistical computer software packages offer the user a choice of the pooled formula or the unpooled formula. The pooled formula is in the computer packages is the first formula, in which equal population variances are assumed. Excel refers to this as a t-test two-sample assuming equal variances. This is the unpooled formula used when population variances cannot be assumed to be equal. The second one. Excel refers to this as a t-test two-sample assuming unequal variances. Again, in each of these formulas, the populations from which the two samples are drawn are assumed to be normally distributed for the phenomenon being measured. So here's an example for t-test for mu1 minus mu2. It still uses the same process as all the other z-test and t-test as before. So this will be very easy for us to follow for our self-study. T-test for dependent samples. In this slide, a method is presented to analyze dependent samples or related samples. Some researchers refer to this test as the matched pair test. Others call it the t-test for related measures or the correlated t-test. What are some types of situations in which the two samples being studied are related or dependent? Let's begin with the before and after study. Sometimes, as an experimental control mechanism, the same person or object is measured both before and after a treatment. Certainly, the after measurement is not independent of the before measurement because the measurements are taken on the same person or object in both cases. Another example would be data from a hypothetical study in which people were asked to rate a company before and after 1 week of viewing a 15-minute DVD of the company twice a day. The before scores are one sample, and the after scores are a second sample. But each pair of scores is related because the two measurements apply to the same person. The before scores and the after scores are not likely to vary from each other as much as scores gathered from independent samples because individuals bring their biases about businesses and the company to study. These individual biases affect both the before scores and the after scores in the same way because each pair of scores is measured on the same person. Another example of related measures includes studies in which twins, siblings, or spouses are matched and placed in two different groups. For example, a fashion merchandiser might be interested in comparing men's and women's perceptions of women's clothing. If the men and women selected for the study are spouses or siblings, a built-in relatedness of the measurement of the two groups in the study is more likely. Their scores are more apt to be alike or related than those of randomly chosen independent groups of men and women because of their similar backgrounds and tastes. To ensure the use of the proper hypothesis testing technique, the researcher must determine whether the two samples being studied are dependent or independent. The approach to analyzing two related samples is different from the techniques used to analyze independent samples. Use of the techniques previously presented to analyze related group data can result in a loss of power and an increase in type 2 errors if we use this technique or if we use the previous techniques with a related group. The matched pair test for related samples required that the two samples be the same size and that the individual related scores be matched. The following formula to test hypotheses about dependent populations can be used. This t-test for dependent measures uses the sample difference d between individual matched sample values as the basic measurement of analysis instead of individual sample values. Analysis of the d values effectively convert the problem from a two-sample problem to a single sample of differences, which is an adaptation of the single sample means formula. This test utilizes the sample mean of differences, d bar, and the standard deviation of differences, SD. An assumption for this test is that the differences of the two populations are normally distributed. Analyzing data by this method involves calculating a t-value with the formula and comparing it with a critical t-value obtained from the table. The critical t-value is obtained from the t-distribution table in the usual way as we did before. So here's an example of t-test samples, for dependent samples. So it still utilizes the same 8 steps as before, still utilizes the same t-table, but I'm just going to notice that we have the same sample size for the before and after. Of course, that should logically follow, right? So we could study this in detail in our own times. Next off is the z-test for differences of proportion. Sometimes we are interested in studying the variances of a population rather than a mean or proportion. Okay, sorry, wrong line again. z-test for P1 minus P2, or the z-test for differences in proportion. Sometimes a researcher wishes to make inferences about the difference in two population proportions. This type of analysis has many applications, such as comparing the market share of a product for two different markets, studying the differences in the proportion of female customers in two different geographic regions, or comparing the proportion of defective products from one period to another. In making inferences about the difference in two population proportions, the statistic normally used is the difference in the sample proportions, P1 hat minus P2 hat. This statistic is computed by taking random samples and determining P hat for each sample for a given characteristic, then calculating the difference in these sample proportions. The central limit theorem states that for large samples, uh, meaning each of the product of P and Q with their ends should be greater than 5, are met. A Z formula for differences in sample proportions is developed and is stated as follows, right here. The formula can be used to determine the probability of getting a particular difference in two sample proportions when given the values of the population proportions. In testing hypotheses about the difference in two population proportions, particular values of the population proportions are not usually known or assumed. Rather, the hypotheses are about the difference in two population proportions. Note that the formula requires knowledge of the values of P1 and P2. Hence, a modified version of the formula is used when testing hypotheses about P1 minus P2. This formula utilizes a pooled value obtained from the sample proportions to replace the population proportion in the denominator. The denominator of the first formula is the standard deviation of the difference in two sample proportions and uses the population proportion in its calculations. However, the population proportions are unknown. So an estimate of the standard deviation of the difference in two sample proportions is made by using sample proportions as point estimates of the population proportion. The sample proportions are combined by using a weighted average to produce P bar, which in conjunction with Q bar and the sample sizes produces a point estimate of the standard deviation of the difference in sample proportions. The result is seen in the second formula, which we shall use to test hypothesis about the difference in the two population proportions. Testing the difference in two population proportions is useful whenever the researcher is interested in comparing the proportion of one population that has a certain characteristic with the proportion of the second population that has the same characteristic. For example, a researcher might be interested in determining whether the proportion of people driving new cars in uptown CDO is different from the proportion in downtown CDO. A study could be conducted with a random sample of uptown drivers and a random sample of downtown drivers to test this idea. The results could be used to compare the new car potential of the two markets and the propensity of drivers in each areas to buy new cars. Here is an example of a z-test for differences in two population proportions. Again, it still uses the same 8 steps and uses the same framework as how to perform the usual z-test for hypothesis testing. And last but not the least, the f-test. The f-test for population standard deviation 1 and population standard deviation 2, or sigma 1 and sigma 2. Sometimes we are interested in studying the variances of a population rather than a mean or proportion. On some occasions, researchers are interested in testing hypotheses about the difference in two population variances. In this slide, We examine how to conduct such tests. When would a business researcher be interested in the variance from two populations? In quality control, analysts often examine both a measure of central tendency and a measure of variability. Suppose a manufacturing plant made two batches of an item, or produced items on two different machines, or produced items on two different shifts. It might be of interest to the management to compare the variances from two batches or two machines to determine whether there is more variability in one than the other. In testing hypotheses about the two population variances, the sample variances are used. It makes sense then that if two samples come from the same population, the ratio of the sample variances should be about 1. However, because of sampling error, sample variances even from the same population will vary. This ratio of two sample variances formulates what is called an F value. These ratios, if computed repeatedly for pairs of sample variances taken from a population, are distributed as an F distribution. And we could locate those values in what we call an F table. The F distribution will vary by sizes of the sample, which are converted to degrees of freedom. With the F distribution, there are degrees of freedom associated with the numerator and the denominator. An assumption underlying the F distribution is that the populations from which the samples are drawn are normally distributed for X. The F test of two population variances is extremely sensitive to violations of assumptions that the populations are normally distributed. Okay? So we have only one formula for the F test, which is this one. It's just the location of the F value uh, in our F table. So here is an example of an F test for sigma 1 and sigma 2. Still uses the 8 steps. No? The only difference of this one from previous z-test and f-test, z-test and t-test, is that this f-test uses the f-table. And also because it has a different distribution called the f-distribution. Okay. So again, I'm going to post a link on the description on the tables that we are using for the z-test, t-test, and f-test, which we call the z-table, the f-table, and t-table. So in our own times, we could study these examples for us to practice on how to perform hypothesis testing.